This week we're going to talk about interconverting functional groups, especially the kind of functional groups that are derived from carboxylic acids. So we'll start by interconverting acids and esters under acid catalysis. So let me skip to the end first. Under acid catalysis, I can go back and forth in this equilibrium. I can go from an acid to an ester. So again, we can think about this as an equilibrium where an ester or carboxylic acid and an alcohol interconvert with an ester and water. So I can go that way. This second equation, notice, is just the reverse of this top equation. So I can go back and forth from the ester or the acid. And probably the easiest way to do that is to add or subtract water. Right? If I throw a lot of water at it, it's going to want to push it to the carboxylic acid. If I take water away from it, it's going to want to push the equilibrium toward water. That's Le Chatelier's principle. Okay? So it's easy to interconvert carboxylic acids and esters under acid catalysis. And a little bit of acid, sulfuric acid, hydrochloric acid, doesn't matter what the acid is, catalytic. Okay? In the same way, I can actually go between two esters. So I can take an ester and an alcohol and swap it with a new ester and a new alcohol. That's called transesterification, right? Trans from the Latin across. So I'm going across two different esters. So again, I can interconvert between esters or between acids and esters. And I can control what side of the equilibrium gets favored by controlling how much alcohol or water I have, right? So if I flood it with one, it's going to push it the other way. Briefly, how should we think about the mechanism of this reaction? Remember, when you have an acid catalyst, use it first, right? Catalysts are there to make a reaction go. They're often the kind of like initial push to start the crank. And so when you have a strong acid catalyst, it is probably doing something in the first step. And this is no exception. So here I'm starting with my acid and methanol. If I use an acid catalyst, I'm going to protonate my electrophile. Remember, acid catalysts make electrophiles more electrophilic. Okay, so here I'm making this weak electrophile into a very strong, very hot electrophile. This weak nucleophile methanol is now going to come and attack it. Notice it's not MEO plus or MEO minus, right? It's not a base. We're in acidic conditions. In acidic conditions, there will not be any methoxide. Okay, no strong bases in acid. So here, again, I have my really hot electrophile. This is going to attack it. I'll get to this tetrahedral intermediate here. This will lose this acidic proton, probably to solvent, but maybe to a molecule of this. And we'll get to this neutral tetrahedral intermediate. These are not stable. Molecules like this are not stable. They want to break down one way or the other. Again, all these steps are reversible. But it's just as likely that my OH, which of these things will grab a proton? Well, if I grab a proton here, it goes up. If I grab a proton between one of these OHs, it goes to this path. Okay, and so now I've protonated an OH to give me a good leaving group, water. This water is going to leave to give me this intermediate, which again, something will swim up and take that extra acidic proton, maybe solvent, maybe something else, to give me this. And I've drawn it like this so you can see the parallels between the sort of two halves of the reaction. Okay, so this is a more or less quasi-symmetric reaction scheme. And you can see that because this is all reversible, I can affect it if I take water away from this by adding some drying agent or something, or just boiling water away, then Le Chatelier's principle will pull all of this equilibrium to this side. However, if I use water as a solvent, I have a lot of water, then I'm going to be pushing everything to the top. just to put a point on it, this is the trans-esterification sequence. So I've just gone around and taken away all my OHs and replaced them with OR, where R is some alkyl group, ethyl, propyl, whatever, right? So here the symmetry should look even more apparent, but the idea is the same. I protonate my weak electrophile, my nucleophile comes in, I get to some tetrahedral intermediate that's not very stable. If I protonate, this OR group here, I can go to this intermediate and get to that. If I protonate my OH here, now I get to some other intermediate that kind of looks like this, but isn't stable. And so could OH take a proton? Yes, it could, but it really doesn't take me to any stable product that I could fish out. Can I hydrolyze amides under acid? Yes, I can. Sometimes I need some forcing conditions, so I might need to heat it, which might look like 100 degrees Celsius, just boiling water. And I'm gonna need more than just catalytic acid. I'm gonna need excess acid to do this, a pretty high concentration of acid. Why is that? Well, what is happening to the acid in this system? Remember that amines are basic. And so anytime that I am able to make an amine, it's going to soak up a molecule of acid and give me this ammonium salt. And this is more or less irreversible, right? It's going to sit down here. Amines are much, much more basic than amides. Amides are really not basic at all. Okay, so again, will this reaction work? Yes. The mechanism is pretty much exactly the same as I just showed you for hydrolysis of esters. Again, you're going to protonate this starting material and then have your weak nucleophile come in. But the difference is that it's really not even reversible because at the end of the day, the acid is going to pull the amine out of solution here. So there's really no way for this to go backwards. So you might say, okay, I get that acid is going to neutralize my amine. But what if I do this without acid? Can I just do this neutral? Well, no. If I just mix those two things together, I'm not going to get an amide. Carboxylic acids are acidic, right? The acid's right in their name. And so when I take a carboxylic acid and a basic amine like that, it's not going to do any other reaction than just an acid-base reaction. So it's going to make a salt, right? An ammonium salt. So N plus O minus. Even if it's basic, right? If I do it under basic conditions, that just gets me here faster, right? And my nucleophile is not good enough to make a bond with the carboxylate. Finally, can I get between esters and amides? I can. I can even do this under neutral conditions. Usually I would just take the ester and just swamp it with a pretty big excess of the amine. Amines are good enough nucleophiles that I can essentially go right to this intermediate. O doesn't mind being negative and N doesn't mind being plus. So this is a reasonable intermediate. If I've got excess amine here, then this amine will take this acidic proton in the tetrahedral intermediate. And so that will get me to this. Now, in terms of leaving groups, oxygen is a way better leaving group than nitrogen is. Because it's more electronegative. You think of O minus being a much weaker base than N minus. So O is a better leaving group than N if they're both neutral like that. So here I'm going to lose the MEO, which is essentially going to be methanol, right? It'll take this extra acidic proton back maybe. And so this is my equilibrium at the end of the day. Again, I can do this under neutral conditions. If I add catalytic acid or catalytic base, it would probably improve it in both ways. But it works fine under neutral conditions. And it's going to, the equilibrium is going to favor the amide just because amides are much more stable than esters. Remember, this lone pair on nitrogen can kind of feed into that pi system. So amides are chemically more stable, lower potential energy. And so this equilibrium is going to favor amides. To summarize, these two reactions are opposites of each other. So this I don't think I named earlier, but this is the Fischer esterification. when you take a carboxylic acid, combine it with an alcohol under acid catalysis to get an ester, and remove water usually at the end. If I were to add excess water, that would push it toward this backwards equilibrium where the ester would go back to a carboxylic acid. We can also think about transesterification, where one ester gets turned into a different ester by adding that other alcohol. With amides, I can hydrolyze them under acid conditions, right? So heating this up in water would give me this. This equilibrium is driven by the fact that this amine gets taken out by the acid, right? So this is not a reversible reaction because I don't really have any amine. All I have is ammonium down here. Okay. Finally, if I treat an ester with an amine, that sets up an equilibrium with the amide in the alcohol here, and because amides are typically more stable than esters, this amide is going to be favored at equilibrium. Okay, so this is a lot of stuff under acid conditions and neutral here. In the next video, we'll talk about some basic conditions where we interconvert these same things.